Okay, hello everybody. Welcome to the supplement for week 2. The plan for today is to discuss 13.3 and 13.4 on arc length and curvature and motion in space, velocity and acceleration. Most of our time today will be spent on 13.3. We'll see the 13.4. We're not going to cover everything that's in the book. We're going to hit the most important points, and we'll also see the 13.4 ties in pretty closely with stuff that we'll have covered in 13.1 through 13.3. So it won't be too big of a leap for 13.4. This will wrap up chapter 13. That'll wrap up the material for this week. And then next week, we'll start into chapter 14. So starting with 13.3, arc length and curvature. Remember from Calc 2 that the length of a plane curve parameterized by x equals f of t, y equals g of t is given by this formula. And remember that we essentially got this formula by taking the curve, splitting it up into a bunch of small segments, approximating each segment as a straight line, and going from there with Pythagorean identity and using linear approximations. So, and then of course, gluing it all back together, taking a limit, and getting an integral. For a space curve, for a three-dimensional curve, it's essentially the same process. Here we have x, y, and z equals h of t as well. And the arc length is the square root of f prime squared plus g prime squared plus h prime squared dt. And we might notice that we could think of having a vector r with components f, g, and h, a vector function r. And for that vector function r, this square root here is just its length. So we can really think of the arc length as integrating the length of r prime. So r has components f, g, h, r prime has components f prime, g prime, h prime, and this is just the length of r prime for our integrand here. So let's take a look at example 1 here. Here we have a curve r of t equals e to the t, e to the negative t, square root of 2t. This curve is parameterized for t in 0 to 2, and we want to find the arc length of this curve. So let's start by finding the integrand, finding the square root. We'll simplify that down first, and then we'll take the integral. So I need the square root of f prime squared plus g prime squared plus h prime squared, or the square root of my first component, e to the t. I take its derivative, it's e to the t, and I square that. That's e to the 2t. My second component, e to the negative t, its derivative is negative e to the negative t. Squared is positive e to the negative t. Sorry, positive e to the negative 2t. And then my third component, square root of 2 times t, its derivative is square root of 2. I square that, and it gives me 2. So that's what I have under my square root. And there's a couple of approaches I could take here. I could use a more algebraic approach. I could use hyperbolic trig functions. Just as a quick review of hyperbolic trig functions, maybe we'll go that route. So I notice that e to the 2t plus e to the negative 2t is almost cosh of 2t. But what would I need? I would need a factor of 1/2. I need a 2 on the bottom here. And I could put that in as long as I have a factor of 2 in front as well. So what does this give me? This gives me 2 cosh of 2t plus 2. And then I can factor out that factor of 2. Cannot come all the way outside the radical. Now, cosh of 2t, one of my hyperbolic trig identities, my double angle identity, cosh of 2t is 2 cosh squared of t minus 1. Looks very similar to the trig identity. And then I have a plus 1 that's still there. So this minus 1 and plus 1 cancel out. my square root of 2 hits the other square root of 2 and just makes a 2. And then square root of cosh square root of t gives me cosh of t. So this is what this whole square root, this whole integrand turns out to be. It's just 2 times hyperbolic cosine of t. As kind of an aside, if you didn't quite remember your hyperbolic trig identities or didn't recognize this as something close to the hyperbolic trig function, we could use algebra here. We could note that e to the 2t is e to the t squared, that e to the negative 2t is e to the negative t squared, and the number 2 I can write as 2 e to the t e to the negative t, and I might recognize this as a perfect square, e to the t plus e to the negative t all squared. I could go that route as well. It's just a question of whether you want to wrap these exponentials under the hyperbolic trig function or not. But we do see that the integrand is 2 cosh of t. And now what do I want to do from my arc length? I need to integrate from 0 to 2 cosh of t dt. The integral of cosh of t is sinh of t. I still have a 2 there, and this is going from 0 to 2. Sinh of 0 is 0. So this is 2 sinh of 2. And that's my answer. Or if I wanted to write it out, this would be 2 times e to the negative 2, or e to the positive 2 minus e to the negative 2 over 2. These would divide out. So I have e squared minus e to the negative 2. I could write my arc length either way. Okay, so leading into, this was leading into the arc length function. So again, let's think that C is a space curve that's given by this parametric representation, f of t, g of t, h of t, for the components of R. And here we'll suppose that R prime is continuous and that C is traversed exactly once. Then we define the arc length function of R. We denote it by S, and we say that S of t equals the integral from a to t of the length of R prime, or the integral from a to t of these derivatives. Here we're using a dummy variable u because the variable t is the input into the arc length function. So what is this really saying? This is saying we're constructing a function that measures the length of the curve along the curve in 3 dimensions, starting at the point on the curve where t equals a and progressing to some point t. So we're measuring the length of the curve along the curve. This can be a very nice thing to do in certain situations, which we will see coming up here in a few minutes. Okay, so example 2, let's reparameterize the curve r of t equals e to the t, e to the negative t, square root of 2 times t. Right now it's parameterized in terms of t, which is just kind of an arbitrary parameter. It doesn't have, it's not super closely tied to the curve itself. But let's reparameterize it with respect to arc length, measured from the point 1, 1, 0. And we want to go in the direction of increasing t. Well, 1, 1, 0, we note corresponds to t equals 0, as can clearly be seen by setting root 2 times t equal to 0 for the third component. So we want to start at t equals 0 and progress forward. Okay, so we have our arc length function. S is going to be the integral from 0 to t of length r prime of u du. Or we know that length r prime of u is just from up here. This is the same space curve that we dealt with in example 1. So it's going to be 2 cosh of u. Integrated from 0 to t du. And this is, of course, 2 sinh of u evaluated from 0 to t. And just like before, sinh of 0 is 0, so we get 2 sinh of t. So this is the S represents the length of our curve from t equals 0 to a given value of t. Okay, so let's take a look then at curvature. So recall that the unit tangent vector was given by t of t equals r prime over length r prime. So it's the vector in the direction of r prime that's the unit vector. We can define the curvature of a space curve as follows. Essentially, we want to take the derivative of t. We want to take something like the second derivative of position to get curvature. That kind of seems consistent with what we know from Calc 1, where things like concavity were related to the second derivative. So that seems to be a plausible idea. But a couple of things here. One, we're not just using r prime, we're using t, we're using the unit tangent vector. So we want to use a unit vector for this. And we're differentiating with respect to s. We're differentiating with respect to the arc length. So dt ds, we could write this in terms of a common parameter t, little t, as d big T, d little t, over ds dt. Or we could think of that as, well, d big T, d little t is t prime of t. And ds dt, well, if s is the integral 0 to t of length r prime, then by the fundamental theorem of calculus, ds dt is just length r prime. And in the book, there are some calculations shown that show that you can rewrite this as length r prime cross r double prime over length r prime cubed. So that's another formula that might be useful in some contexts. Okay, so let's try to find the curvature of a circle with radius rho. Here I'm using radius, the Greek letter rho, looks kind of like a P, because we're already using r to represent our vectors up here. So let's suppose that we have a space curve, r bar of t equals rho cos of t, rho sine of t, and then we'll just say some number k for the third component. So here in a plane z equals k, a plane parallel to the xy plane, we just have traced out a circle of radius rho that's centered at the z-axis. Okay, so how can we find this curvature? Well, one way we could go about it is reparameterizing it in terms of s, in terms of the arc length, and going from there. So if I think in terms of my xy plane, or a plane parallel to my xy plane, I know that I have a circle of radius rho. And what does the variable t represent? Well, the variable t represents an angle with the x-axis. right? X equals rho cos t, y equals rho sine t. That is just the description of the unit circle in polar coordinates. And I also know that the arc length traced out from t equals 0 to t equals t. Well, for an angle t on a circle of radius rho, my arc length is just the angle times the radius is just rho times t. We're, of course, taking t to be in radians here, so that all of this works out nicely. So S equals rho t, or in other words, t equals S over rho. So writing r in terms of S gives me rho cosine of and t equals S over rho. For my second component, rho sine of S over rho. And my third component is still just the constant k. Okay, so then what is dr ds then? Well, this is just the derivative of r when it's written this second way, when it's written with respect to s, the arc length. So dr ds is going to be, well, if I differentiate my first component with respect to s, I get a cosine differentiates to negative sine of s over rho. A factor of rho pops out, but that cancels with the rho in front of the cosine. For my second component, sine of s over rho differentiates to cosine of s over rho. And again, I get a factor of 1 over rho popping out from the chain rule that divides out the rho in front. And k is just a constant. It differentiates to 0. So this is dr ds, or r prime of s. And we note that the length r prime of s is 1. Right? The length will be the square root of first component squared, sine squared of s over rho, plus cos squared of s over rho plus 0. Square root of 1 is 1. So what's my unit tangent vector in terms of s, in terms of the arc length? Well, it's dr ds over the length of dr ds, or that's just dr ds. So that's my unit tangent vector written in terms of s. And now I don't have to use any of these formulas that have the t's in them. I can just directly use my curvature formula. dt ds, take the length of that. So what is dt ds, or big T prime of s? Again, if I differentiate the first, the sine differentiates to a cosine. And I get a factor of 1 over rho that pops out. Differentiate the second component, the cosine differentiates to a negative sine. And again, a factor of 1 over rho pops out, and still 0 for my third component. And then finally, my curvature. As an aside, the curvature is denoted with the Greek letter kappa. So my curvature, kappa, is length dt ds, or I see that I'm going to get cos squared of s over rho plus sine squared of s over rho. That's going to give me 1, but I'm going to have a factor of 1 over rho, or 1 over rho squared inside the radical. When it comes out, it's going to be a 1 over rho. So I see that the curvature of a circle with radius rho is 1 over rho. So if I have a smaller radius, that's a circle that kind of has to bend faster, that's kind of more curvy, right? If you were walking around that circle, you have to reorient yourself more quickly. So for a smaller row, that's a higher curvature. That means it curves more. It means I have to keep turning more aggressively to stay on that circle. For a circle with a larger radius, I know that that kind of locally seems flatter, right? It seems straighter. For a larger radius, larger row, I'm going to have a lower curvature. So this is in line with my intuition. Okay, let's look at another example. Find the curvature of a straight line in space. So I think our intuition suggests that, well, a straight line shouldn't be curved. A curvature maybe should be something like 0. Or maybe if we went a little more abstract, we might think of a straight line as being like, a circle with maybe something like an infinite radius. If I think of as rho goes to infinity, what happens to my curvature up here? Well, that goes to 0. So I kind of have a feeling that this should be 0. Can we actually make that work out? Okay, so let's look at the curvature of a straight line. So let's just take our curve to be R naught plus TV. Here, R naught and V are constant vectors. R naught is the position or location vector, and V is our direction vector for our line. And here we'll also assume that our direction vector V is not the 0 vector. That would be a bit silly to have a direction vector being just the 0 vector. So we'll assume that, but I don't think that's a big surprise. So what's R prime of t? Well, I see that R naught is just a constant vector. It just differentiates off. And then I have t times v prime. R prime is just, or sorry, t times v. R prime is just v. What is my unit tangent vector in terms of t? Well, that is v over length v. Remember, v is constant. So there's just v over length v. Some other constant vector is just a rescaling of the constant vector v. And what is t prime? Well, this is the 0 vector. So t prime is the 0 vector. I think pretty clearly we can see that the curvature is going to be 0, but let's go through carefully. T prime is the 0 vector, but I mean, I suppose it could be the case that ds dt is 0 as well, and I get some kind of indeterminate form or something. Let's just check ds dt. So what is ds dt? Well, remember up above, so if s is the integral a to t of length r prime, ds dt is just length r prime. But what's length r prime? That's just length v. And because v is not equal to not the 0 vector, this is non-zero. Okay, so my curvature, which is length t prime over length r prime, is what? The 0 vector, the length of that, over the length of v, which is just 0. So my curvature of a straight line in space, I have verified is 0. That's also consistent with my intuition. Okay, and then for this last example, let's take a look at kind of a less trivial example. Find the curvature of this curve where the components are 2t, t squared, and negative 1/3 t cubed, with respect to its parameter t being bigger than or equal to 0. Okay, so I have r, and in this case, I'm going to use, so I gave an example using the first formula, an example using kind of whatever way you want to look at using this second formula here. Let's look at an example using this third formula. So I'll actually copy this formula down here. This is the formula we're going to use. So I have r, I need r prime and r double prime to plug into this formula. So r prime, derivative of 2t is 2, derivative of t squared is 2t, and derivative of negative 1/3 t cubed is negative t squared. The second derivative is 0 for the first component, 2 for the second component, and negative 2t for the third component. Okay, now there's two things that I need. I need this big cross product thing in the numerator, taking the length of that, and then I need the length of r prime. Let's get the cross product out of the way. So let's figure out what is r prime cross r double prime. So here we set up our matrix. R prime has components 2, 2t, and negative t squared. And r double prime, 0, 2, and negative 2t. And again, we can use our kind of diagonals trick. Make this a little quicker. So I see that going down the main diagonal, I have I times 2t times negative 2t. So that's a negative 4t squared. J, when I wrap around, I'm going to get j times negative t squared times 0. That gives me a 0. And then k times wrapping around 2 times 2 gives me a 4. And then I have to go the other way, the off diagonals, going wrapping around the other direction. This comes in with a minus, so I have minus I times negative t squared times 2. So that's a plus 2t squared. The negative from going the other direction cancels with the negative on the negative t squared. For j, again, I get a negative j times 2 times negative 2t. So that's a plus 4t. And then for k, going top right to bottom left, I end up multiplying by 0. So that gets me a 0. Or r prime cross r double prime is the vector with first component negative 4t squared plus 2t squared is negative 2t squared. Second component is 4t. Third component is 4. And for my numerator, I need the length of this vector. So that's going to be the square root of what? I need to square each of my components, so I get 4t to the fourth plus 16t squared plus 16. I suppose I can factor out a factor of 4, make this a little easier to do the algebra. So this gives me t to the fourth plus 4t squared plus 4. And I recognize this as a nice perfect square. I see that this is going to be t squared plus 2 all squared. The first obviously give me t squared is t to the fourth. My lasts give me 2 squared is 4, and my cross terms give me 2 times t squared. So that all checks out. And this just gives me 2 times t squared plus 2 once the square root gets rid of that squared. Okay, so that all is my numerator. And now I need my denominator. My denominator, nicely enough, isn't all that difficult to do. It's just length of r prime. Maybe I'll try to put that over here so we can keep everything on the screen. Length r prime is, again, the square root of the sum of the squares of the components. So that's a 4 plus 4t squared plus t to the fourth. And again, I recognize this as a perfect square. I see that this is 2 plus t squared, all squared. Right, the 2 squared gives me a 4, the t squared gives me a t to the fourth, and the cross terms give me 2t squared twice, 4t squared, or this is just 2 plus t squared. I guess I don't need the parentheses, but there they are. And I need this to the third power, 2 plus t squared cubed. I noticed that one of these cancels with one in the numerator, leaving me with a curvature of, after all is said and done, 2 over 2 plus t squared squared. So again, a couple different ways to find the curvature, a few different formulas to use, a few different ways to approach these problems. The first one was fairly easy to write, to reparameterize in terms of the arc length, so we went that route. This third one I think was easier to just kind of, do the sledgehammer approach, just crank out this somewhat annoying cross product, but that was really the bulk of the work. And of course, you probably have noticed that the arc length function, just like in Calc 2 in 2 dimensions, is not a very nice function. To be able to get an integral that you're actually able to compute reasonably by hand, the problems need to be, constructed just right. So if you take just kind of some arbitrary space curve, you're probably not going to be able to do the integral by hand. You would have to use a calculator or something, or a computer to get an estimate to what that function is for a certain input. But you can tell that some of these problems are constructed so the things work out kind of just right. So we get nice perfect squares under the square roots, things like that. Okay, so moving on to the next section here, the normal and binormal vectors. Okay, so first thing that I want to review is this lemma, this small theorem that's going to help us in a minute here. And it says that if length r is constant, then r prime is orthogonal to r. So if the length of a vector is constant, then its derivative is orthogonal to it. Okay, so let's look at a proof of that. Okay, so if we have length rc a constant, then that tells me that the dot product of r with itself is c squared, also a constant. And that means that the derivative of this dot product with respect to t has to be 0. So on one hand, the derivative of this dot product is 0. On the other hand, the derivative of this dot product is going to be what? It's going to be r prime dot r plus r dot r prime, just applying our product rule for the dot product, or this is just 2 r dot r prime. The dot product is commutative, so we can just switch the order, add them together. And of course, if 2 r dot r prime is 0, then r dot r prime has to be 0. And therefore, r is perpendicular to r prime. Okay, so if we have a vector whose length is constant, then its derivative is orthogonal to itself. Well, we remember that the unit tangent vector was constructed to be a unit vector to have length 1 always. So a consequence of the previous lemma is that t prime is orthogonal to t. So t prime is a vector that is normal to t, the unit tangent vector. So we'll use it to define what we'll call the unit normal vector. Now, if I think of any vector, but specifically a tangent vector, the unit tangent vector, if I am looking for a vector normal to it, there's a whole bunch of vectors normal to it. So, but this particular vector here is what we're going to call the unit normal vector. So there are a bunch of vectors that happen to be normal to t of t, but this specific one, we denote the unit normal vector. We give it the symbol n of t, and it's t prime over length t prime. T prime over length t prime, or, well, what was our curvature? Kappa was like dt ds, length of that. So we could really think t prime over length t prime is like dt ds over length dt ds, just in a different parameterization, parameterizing based on arc length. Or in other words, it's kind of the rate of change of the tangent vector with respect to the arc length. Okay, so that is our definition for our unit normal vector. What does our unit normal vector kind of mean? What is its descriptive representation? It indicates the direction in which the unit tangent vector is something like turning or moving. This is analogous to something like the second derivative in real valued functions, where it indicates, in a sense, the direction in which the tangent lines are moving, or the slopes of the tangent lines. Are they getting steeper or less steep? Since n and t are orthogonal, we can actually find a third vector orthogonal to both, and then we'll have 3 vectors that are all orthogonal to each other. And this set of 3 vectors can actually act as a frame of reference. It can act as kind of a new coordinate system that's somehow more inherently tied to the space curve, right? Our 3-dimensional coordinate system ijk is kind of just fixed. It doesn't really have anything to do with any given specific space curve. But we could look at a different coordinate system related to n, t, and this third vector, and we can see that that's a similar coordinate system, 3 orthogonal vectors, and it's inherently tied to the space curve that we're studying. This can be a very nice thing to have. So this third vector we construct, you probably could guess, by taking the cross product of the unit tangent vector and the unit normal vector to give us a third vector that is perpendicular to each of the other 2. We denote it with b of t, and we call it the binormal vector. And so, roughly speaking, in this frame, t represents kind of your forward direction. If you're sitting on this curve and moving along it, t is kind of your forward direction. n is the direction that you're turning. And if we think of t and n, those two vectors construct a plane. And we could be moving along a curve that stays in that plane, or we could be moving along a curve that moves out of that plane. And b, the binormal vector, represents the tendency for a path to twist or out of that plane. So we'll see that it's related to an idea called torsion near the end of the lecture. So again, t represents kind of our forward direction, our like instantaneous motion. N represents the direction we're turning, and then b, our tendency to twist out of that plane defined by t and n. The plane defined by the normal and binormal vectors is called the normal plane. It's the set of all vectors orthogonal to the tangent vector. And the plane defined by t and n is called the auscultating plane. And we'll see that it actually has an important role to play a little bit later on in section 13.4. Okay, so let's look at example 6. Okay, so example 6, let's find the unit tangent vector and the unit normal vector for the circle with radius rho given here. The x component is rho cos of 2t, y component rho sine of 2t, and z component we'll just take to be 0. And we'll also find b, the binormal vector. All right, so we know that the unit tangent vector is r prime over length r prime. So what is r prime? It's going to be negative 2 rho sine of 2t. For the first component, the second component, 2 rho cos of 2t, and third component 0. Length r prime, we see we're going to get a sine squared plus cos squared bit under the radical, so that's going to be 1. Length r prime is just going to be 2 rho. And t, therefore, is going to be, well, r prime over 2 rho, it just cancels out those 2 rho coefficients. This is going to be the vector negative sine of 2t, comma, cos of 2t, comma, 0. So this is my unit tangent vector. Okay, so what about my unit normal? Well, that's t prime over length t prime. Just kind of doing this derivative process a second time. So what's t prime? Note that we're taking t prime here, not r prime prime. So t prime. So we differentiate negative sine of 2t. That gives me negative 2 cos of 2t. For the first component, gives me negative 2 sine of 2t for the second component, and still 0 for the third. And what is length of t prime? That's going to be 2. So t prime over length t prime is going to be negative cos of 2t, negative sine of 2t, 0. And that is my unit normal vector. And a couple of things to note here. Note that my unit normal vector is just negative rho times my original position vector. The normal vector is just pointing in the opposite direction of my position vector. It's in a sense pointing towards, if I think of my XY plane here, with the circle, my position vector R looks like this. And my unit normal vector looks like that. It might be a little bigger or smaller than, it might have a greater or lesser magnitude than R, but it's in the opposite direction. It's pointing towards the center of the circle. I also remember that T is perpendicular to N, and therefore T is perpendicular to R as well, because N is parallel with R. So my unit tangent vector is perpendicular to my position vector. Okay, and then let's find B, the binormal vector. So again, if we remember the roles of each of these, the T says what direction am I moving in? That's the tangent vector. N says what is my unit normal? That kind of says how is the tangent vector changing? That's something like the second derivative, the kind of derivative in a sense of the tangent vector. Those are orthogonal. And then the purpose of B is to give me a third vector to be able to create a new 3D coordinate system that is shifted or rotated, that is really inherently tied to my space curve. So what's the formula for my binormal vector? Again, it's T cross N in order to give me a third vector that is orthogonal to each of the other two. Okay, so what is T? It has first component negative sine 2t, second component cos 2t, third component 0. And what is N? First component negative cos 2t, second component negative sine 2t, and third component 0. Should have left myself a little more room there, but and again, I can do my little shortcut method here. I see that I, going down this main diagonal, is going to be multiplied by cos 2t times 0, so that's going to be a 0. J is going to be multiplied by 0 times negative cos 2t, that's going to be a 0. K is going to get multiplied by what? Negative sine 2t times negative sine 2t, or that's sine squared of 2t. Those are my three kind of main diagonals going top left to bottom right. And then the three off diagonals going top right to bottom left come in with negatives. So for I have negative I times 0 times negative sine of 2t, that's 0. For j, I have negative j times negative sine 2t times 0, that's also 0. And for k, what do I get? I have negative k times cos 2t times negative cos 2t, that is plus cos squared 2t, or my binormal vector is 0, 0, 1. Or in other words, my binormal vector is just the vector k. My binormal vector, if I look back up here at my picture, this is looking down like parallel to the z-axis. That's where my unit tangent and unit normal vectors are pointing. And my binormal vector would be kind of like pointing right back up at me. My binormal vector would be looking down, I would just see that vector pointing straight back at me. Okay, so let's introduce just another, this is a very minor point, but you might be looking at this and saying, wait, my binormal vector is k, and I know that it's supposed to be somehow related to the tendency of my path to twist out of the plane defined by t and n, but it kind of seems like my path is just staying in the tn plane. Why didn't I get a binormal vector of 0, of all zeros? It kind of seems like something went awry here. Well, it's not exactly the binormal vector that gives us that twisting idea. It's this idea called the torsion. And this is a side note. I'm not sure if this is even in the Stewart book, but just kind of aside to make this bit make a little more sense. The torsion is just as convention is defined with a negative. It's dBds dot n dot the unit normal vector. And we can clearly see that dBds is going to be 0, but also if we dotted even just b against n, we see that anywhere that there's a component, a non-zero component for n, there's a 0 for b and vice versa. So we can immediately see that this is just going to be 0. So our tendency to kind of twist out of this plane, this is really what we're talking about there. This is how we would use the binormal vector to define that torsion, that idea of twisting out of the plane of t and n. And we see that from the picture, we're obviously not twisting out of that plane. We're just staying in that plane, going around that circle. And our torsion indeed is 0. Okay, so then moving on to 13.4. So 13.4, motion in space, velocity, and acceleration. So here the context we're thinking of is we're thinking that this vector function r of t, rather than just representing some space curve that could mean anything or essentially mean nothing, we're thinking of representing the position of a physical particle moving through space. We can then define the following quantities. We can define the velocity of the particle. V of t is r prime of t. It's the rate of change, the time rate of change of the position. Note that velocity is a vector quantity. It has both magnitude and direction. And we call the magnitude of velocity the speed of the particle. So speed is the magnitude of the velocity, or its length r prime. And the acceleration of the particle is, again, the time rate of change of velocity, or the second time derivative of position. Right, familiar definitions from Calc 1, but they do apply in a very similar way in Calc 3 here. The main differences being that velocity and acceleration are vector quantities here, and speed is the length of the velocity vector. As kind of a little side note, we can also think of speed in relation to arc length. So here we're thinking in terms of some parameter t that is kind of more inherently tied to something like the 3D coordinate system. But we saw that arc length was more inherently tied to the curve itself. We know that arc length is the integral of length r prime, but we said that length r prime is just length v, it's just speed. In other words, to find an arc length, we're integrating speed. Or in other words, to compute distance traveled, the arc length, we integrate speed over time. So that's another interpretation of arc length. We're finding a distance by integrating a speed over a time. And then last little note here, Newton's second law in vector form says that F equals ma, where here a is the acceleration vector, and therefore F, the force vector, is also a vector quantity. It has magnitude as well as direction. Here F is the force acting on a particle, and little m is a scalar that represents the mass of the particle. So this is good old F equals ma, just where acceleration and force are vector quantities instead of scalars. Okay, so let's look at this example. Similar to our previous example number 6, consider a particle moving in the circular path. Let's find the velocity, speed, and acceleration of the particle, and we'll kind of we'll actually just revisit this picture, but under a different context, and maybe this will lead to some interesting physical intuition, or maybe counterintuitive physical intuition. Okay, so I want to find the velocity, speed, and acceleration, so I need to find r prime, but again, I already found r prime up here. I just have that over here. I wonder if I can actually lasso select this and get it to work. Fingers crossed. It looks like I missed a bracket, but so just from up above, this is what r prime is. Or in other words, this is just the velocity vector. So what is the speed of our particle? It's length v, or in this case, it's going to be 2 rho. That kind of makes sense. If I have a circle with a bigger radius, I'm parameterizing that circle basically according to angle. So if I'm covering a constant angle per unit time, a circle with a bigger radius, I have to travel faster to make up that ground. What about acceleration? Well, acceleration is the derivative of velocity. Now up here, we didn't quite compute our double prime. We computed t and then t prime. So we don't want to just grab this over here. We will compute compute acceleration from velocity by taking another derivative. When I differentiate again, I get another factor of 2 that pops out. So I get a negative 4 rho cos of 2t, negative 4 rho sine of 2t, comma 0. And I actually notice that this is negative 2 squared times r. Right, the negative comes from the 2 derivatives from the trig functions. The 2 squared comes from the 2 derivatives, each popping out a factor of 2 from the chain rule. And r is the base off of which we were working. So my acceleration vector actually looks like negative of my position vector. So again, in the xy plane, I have a circular path. I have a position vector, r. I have an acceleration vector, a, that is going in the opposite direction. But I also know that F equals ma. So my force vector is also in this direction. M, of course, being mass, is a positive number. And then, of course, my unit tangent vector is here, and that is my velocity vector in this case. I said unit tangent vector, but this is just a tangent vector. It's not necessarily a unit vector. My tangent vector is my velocity vector. But I actually noticed that if this particle is just, if I was thinking of it being tied to the end of a rope and I was swinging it around and then I just let go at this point, if I just, severed whatever cord was holding it whenever it was spinning around and it hit this point and I just cut that cord that was making it stay in a circle, well, my particle would just continue along this straight line in the direction of v, in the direction of the velocity vector. So then what force do I have to apply to the particle to make it keep going around the curve? A lot of people would, and I think the intuitive answer is I have to apply a force like in the direction of v to make it keep going around the curve. But actually what we're seeing here is the force that I have to apply is in the direction of pointing directly toward the center of the circle. So there's those, I don't know, 1500s or whatever, like pictures of, you have like the sun here and then planets going around and there's like, little angels. You can tell I'm not an artist, but little angels like pushing the planets this way. But really the angels should be pushing the planets that way, right? Directly towards the sun. That's the direction they would have to push the planets to make them stay in, say, more or less a circle. So my acceleration or my force is directed towards the center of the circle in order to maintain this circular path. And if at any point I was to lose that force that's keeping me directed towards the center, if that were to go away, then my particle would just continue along that velocity vector. And I think this is intuitive when we think about it in terms of like taking a ball at the end of a cord and swinging it over our head. We kind of realize that as I swing it around, the cord is being pulled in the direction that the ball is from my hand. It's being pulled perpendicular to the direction the ball is moving. And if I were to cut that cord, the ball would move in the direction that it keeps moving, that it's instantaneously moving at that point. But I think this is, often surprising that to maintain a circular orbit, we need to pull towards the middle of the circle, not tangentially along the circle. Okay, and then the last bit that we're going to discuss in this section is the idea of tangential and normal components of acceleration. And the details for these calculations are in the book. We're hitting some of the high points in section 13.4. We're not going over all of the Kepler's law stuff that they go over, but just covering some of that material, the important, more foundational stuff. So again, recall the unit tangent vector, and we can rearrange the relationship of the unit tangent vector to the velocity vector to see that velocity is the length of velocity times the unit tangent vector. Your book kind of makes this length of velocity the symbol non-bold v, but because that can be pretty hard to tell the difference on a computer screen, and especially because OneNote occasionally does drop some of my formatting, I didn't want to rely on that too heavily. So like here, especially in small font, it's very difficult to tell the difference between bold and not bold. So I've just maintained the notation length v for speed. Let me move that down so we can see it a little better. Yep, see there, lost my formatting. So we have now a formula for v of t. If we differentiate and apply the product rule, we get the derivative of the speed times the unit tangent vector plus the speed times the derivative of the unit tangent vector. And with a little bit of manipulation, we can come down here and see that the acceleration vector is derivative of speed times unit tangent vector plus this other bit here, which is the curvature times the square of the speed times the unit normal vector. And kind of as an aside, this is why we really want these to be unit vectors, because it makes things like this so much easier to interpret. We can really break, say, an acceleration vector down into its components when we're moving along in the directions of unit vectors. Makes it much easier to just write those components out. So we're going to call this the tangential component of acceleration. That's going to be the derivative of speed. And the normal component of acceleration is going to be this curvature times the square of the speed. And as an exercise, I mean, these formulas aren't too terrible, but maybe it seems kind of arbitrary. Maybe the tangential component of acceleration being the change of speed, maybe that makes a little bit of sense, but the normal component maybe doesn't make so much intuitive sense. As an exercise, derive the following formulas using the ones above. That the tangential component is the dot product of the vector of the velocity and acceleration vectors over the length of the velocity vector. And the normal component is the cross product, well, the length of the cross product between the velocity and acceleration vectors over the length of the velocity vector. Again, remember from chapter 12 that kind of roughly speaking, the dot product is a measure of how parallel two vectors are, and the cross product, or really the length of the cross product, is kind of a measure of how perpendicular two vectors are. So the more that our acceleration vector is in line with the velocity vector, the greater the tangential component and the lesser the normal component of acceleration. When our acceleration vector is right in line with the velocity vector, our normal component's actually 0, and we don't tend to turn at all. We just kind of stay in a straight line. Okay, so last bit here, last exercise or example, let's find the tangential and normal components of velocity for the following position function, which describes a helix. Here we have r of t is b cos t, b sine t, and c times t. All right, so that's my vector r. I would like to use these formulas. So I have a position vector, I need velocity and acceleration to use those formulas. What's my velocity vector? Well, the derivative of b cosine of t is negative b sine t. Derivative of b sine t is b cos t, and derivative of ct is just c. My acceleration vector, I differentiate again. I get negative b cos t. I get negative b sine t, and then 0 for my third component. I can find, I guess, length v. Let's just get that out of the way. Length v is going to be the square root of, well, b squared sine squared t plus b squared cos squared t. That's just b squared. And then plus c squared. So that's length v. That's my speed, square root of b squared plus c squared. All right, so for my tangential component of velocity, let's find the dot product, v dot a. So for the tangential component, we'll first find v dot a. And I see this gives me what? Well, just I multiply my first two components, first of v times first of a. That gives me positive b squared sine t cos t. I multiply the second components, negative b squared sine t cos t. And then I multiply my third component, c times 0. And I see I actually get 0. Remember, the dot product gives me a scalar out, right? So the numerator is 0. The denominator is b squared plus c squared under the radical. So presumably that's non-zero. If b and c were both 0, then r is just 0 everywhere. That doesn't really make an interesting space curve or really a helix. So we'll take it to be true that not both b and c are 0. But we see our dot product is 0. So our tangential component of acceleration is 0. There's nothing pushing this particle kind of in the tangential direction or pushing it more in the direction that it's headed at the moment. What about the normal component then? We might have a guess at what this should be, but not quite equals yet. We might have a guess at what this should be, but let's check. So what do I want to do? I want the cross product of the two vectors, v cross a. Start there, I'll take the length and then divide by length v. So v cross a, we have negative b sine t, b cos t, and c, negative b cos t, negative b sine t, and 0. And again, so for I, on my main diagonal here, I have I times b cos t times 0, so that's a 0. For j, I have j times c times negative b cos t. That's negative bc times cosine t. And for k, I have k times negative b sine t minus b sine t, or times negative b sine t again, is plus b squared sine squared t. And now going down my off diagonals, I have minus I times c times minus b sine t. So minus bc sine t. For j, I have minus j times minus b sine t times 0. So that's minus 0. And then for k, I have minus k times b cos t times negative b cos t. So that's plus b squared cos squared t. The minus from going the other direction cancels with the minus and the 1 minus b cos t on the bottom left. Or this is the vector, what? Minus bc sine t minus bc cos t. And then I see down here for my third component, sine squared plus cos squared is 1. So I just get b squared at the end here. I could actually factor out a b. And I see now that length v cross a is going to be b, and let's suppose the b is positive. It's going to be b times the length of this vector, but that's going to be square root of, I get c squared sine squared t plus c squared cos squared t, or just c squared, and then plus b squared from that third component. So what's my normal component of acceleration? It's the length of this cross product, which I just found, divided by length v. Or the normal component of acceleration is b square root of c squared plus b squared over length v, these divide out. My normal component of acceleration is just b. Note, of course, that my length of acceleration vector is just b. So all of that magnitude is going into the normal component. None of it is going into the tangential component. So even for this helix, we don't even have anything kind of pushing upwards. It's just the upwards bit of the helix is just kind of maintaining the velocity that it already has in that upwards direction. There's no acceleration upwards being applied, or upwards meaning in the positive z direction. There's not even any acceleration or force being applied in the tangential direction, like making it, like pushing it around the circle. Again, all of the acceleration, all of the force is being applied normally. It's being applied pushing the particle towards the z-axis, towards that center of rotation, and that's what makes it continue in that circular like path along that helix. Okay, so that wraps up what we're going to cover in chapter 13, 13.3 and 13.4, and wraps up the material for this week. And then starting next week, again, we'll be in chapter 14. So we'll start in the chapter 14 on Monday, continue with the supplement on Tuesday, continue further on Wednesday, and then possibly another supplement at the end of the week.